Hello everyone, my name is Noemi Gyori and I will be presenting our work on how training data distribution impacts the estimation of tissue microstructure with machine learning. I have nothing to declare. Machine learning is an exciting tool that may be used to shorten measurement times by reducing demand on the number of gradient directions or the spatial resolution acquired when scanning. However, supervised machine learning requires training data in order to learn the relationship between inputs and outputs. There are many compelling examples in healthcare technology and beyond that demonstrate that in the absence of balanced training data, machine learning can propagate disruptive biases such as discrimination by race and gender. In diffusion MRI, previous works that use supervised machine learning typically use one of two training strategies. In the first strategy, MRI measurements are obtained, and traditional model fitting is used to estimate parameters. The measurements and parameter estimates are inputs and outputs respectively when training the machine learning algorithm. In the second strategy, parameter combinations are sampled uniformly from the entire plausible parameter space. The diffusion MRI signals are simulated using a forward model, and these are used for training. Importantly, in the two strategies, the machine learning model is trained on two different data distributions: healthy parameter combinations or uniformly distributed parameter combinations. In this work, we investigate the impact of training data distribution on microstructural parameter estimates. We train artificial neural networks on different distributions of ground truth parameters and corresponding simulated diffusion MRI signals. We use a simple two-compartment microstructural model based on the spherical mean technique as an example. This model has only two independent parameters, which makes it easy to visualize the parameter space. We fit this model to a dataset obtained using healthy adult subjects. We train neural networks using two different training data distributions: uniformly distributed parameter combinations and parameter combinations obtained from 5 healthy subjects. In vivo parameter maps using the neural networks in traditional model fitting look similar at first glance. However, when compared with parameter estimates using traditional model fitting, some differences arise, suggesting a difference in the accuracy of the two methods. To further investigate the accuracy of each method, we quantify bias using quiver plots where each arrow points from the ground truth to the estimate. This visualization shows that biases are overall higher for both of the neural networks compared to traditional model fitting. Training on the healthy brain distribution leads to highest overall bias. In particular, when the healthy brain distribution is used in training, biases are high for parameter combinations that are not well represented in the training data. For example, the estimates for the parameter combination shown by the red point is strongly biased for the healthy brain distribution, but not for the other two. Remarkably, when the test data has low SNR, even typical parameter combinations may be strongly biased, as we show with the red points in this example. Worryingly, the machine learning techniques show low variance even in regions of the parameter space where bias is high. This demonstrates that high precision in machine learning can convincingly hide strong biases, and that results obtained with machine learning must be interpreted with caution. For example, machine learning might hide lesions and yet provide convincing smooth maps. To show this, we simulated a tissue abnormality where both parameter values were decreased compared to the surrounding healthy white matter. When SNR is 25, the lesion is visible using both traditional model fitting and machine learning. In contrast, when SNR is low, both traditional and machine learning estimation obscure the lesion. Importantly, however, the maps obtained from traditional model fitting are noisy, indicating uncertainty in the underlying values, while the smooth maps obtained from machine learning may lead to overconfidence in the parameter estimates and erroneously suggest that the tissue is healthy. In conclusion, our results show that while machine learning model fitting gives smooth maps even when SNR is low, this can mask substantial biases and hide lesions. We used artificial neural networks here and as an example machine learning model, but observed similar effects using random forest regressors. Check out these results in our recent preprint available from this link. Thank you for your attention.